Today's challenge is to convert time units on a distant planet. Take about 4 minutes and test your knowledge. Today, we are working with an unusual system of time units. In this fictional model, the exoplanet Kepler 87 uses different units of time than Earth does. Your task is to compare the duration of 1 Kepler second with the duration of 1 Earth second. To solve the problem, you need to connect the given information carefully. Read the problem closely and first try to solve it on your own. If you need a little more time, that is absolutely fine. This is the best way to find out how confidently you can work with time units and unit conversions. Afterward, we will compare the complete solution method and the result together. Do not skip straight to the solution. Instead, work through each step together with me. This way, you will understand not only the result, but also the way of thinking behind this problem. Today, we are working on a problem involving physical quantities and different systems of time units. In this fictional model, the exoplanet Kepler 87 takes approximately 10 Earth hours to complete one full rotation. One complete rotation is called 1 Kepler day. A Kepler day consists of 10 Kepler hours. On Kepler 87, 1 Kepler hour equals 100 Kepler minutes, and 1 Kepler minute equals 100 Kepler seconds. We need to determine the duration of 1 Kepler second compared with 1 Earth second. Before we begin, let's consider the significant figures. The rotation period is given as approximately 10 hours. The word approximately tells us that this value is not exact. For this model calculation, we assume that the rotation period is known to within plus or minus 1 hour. The relative uncertainty is therefore 1 hour divided by 10 hours, multiplied by 100%. This gives us a relative uncertainty of approximately 10%. For the comparison intended here, 10% is quite a large uncertainty. In a real astronomical investigation, the rotation period would need to be measured much more accurately. For this model, we will retain two significant figures as a practical working assumption. Let's begin with the Kepler day. One complete Kepler day consists of 10 Kepler hours. Each Kepler hour contains 100 Kepler minutes, and each Kepler minute contains 100 Kepler seconds. Therefore, we calculate 10 Kepler hours multiplied by 100 Kepler minutes per Kepler hour multiplied by 100 Kepler seconds per Kepler minute. The units of Kepler hours and Kepler minutes cancel out. This leaves us with Kepler seconds. 10 multiplied by 100 multiplied by 100 equals 100,000. So, 1 Kepler day contains approximately 100,000 Kepler seconds. In scientific notation, this is 1.0 times 10 to the power of 5 Kepler seconds. Now, we express the same time interval in Earth units. The complete rotation takes approximately 10 Earth hours. 1 Earth hour contains 60 Earth minutes, and 1 Earth minute contains 60 Earth seconds. Therefore, we calculate 10 Earth hours multiplied by 60 Earth minutes per Earth hour multiplied by 60 Earth seconds per Earth minute. Again, the units cancel out. 10 multiplied by 60 multiplied by 60 equals 36,000. So the same time interval is approximately 36,000 Earth seconds. In scientific notation, this is 3.6 times 10 to the power of 4 Earth seconds. Now we compare the two systems. 100,000 Kepler seconds correspond to 36,000 Earth seconds. To determine the duration of 1 Kepler second, we divide both sides by 100,000. This gives us 1 Kepler second equals 0.36 Earth seconds. The result already has two significant figures. Therefore, it remains unchanged. The important idea here is that units can be treated algebraically in the same way as numbers. This allows us to convert between different systems in a clear and systematic way. At the same time, we must always consider whether the available precision is sufficient for the practical purpose. Not too difficult, was it? See you next time.